today's last talk. The speaker is Professor Hendrik Süß from the University of Jena, and the title is Volumes and Normalized Words.
Yes, let me first thank the organizers, first for inviting me, second for bringing us all together and making this nice conference happen. I will start with actually introducing maybe once again this notion of normalized volume. So we have seen it already today in the morning in the first talk. So say normalized volumes. After GP. Okay, so what is this? So we want to associate an invariant to a singularity. So we have a point, little x, and some variety, capital X of dimension d. And so this definition takes a little bit of time, so we need to go through some steps. And the first step is we need additionally to fix a variation on our functions. So you should think of it as some kind of vanishing order. And once we fixed such a valuation, I want to define what's the volume first of this valuation. And here we look at the subspace of functions which evaluate giving at least k. So we look at our functions such that the valuation applied to f is at least k. Okay, so then we take our local ring of functions and we divide out this subspace. Okay, and everything is set up such that this gives us a finite dimensional vector space. So I can look at the dimension of this vector space, and I'm interested in what happens as I increase my parameter k. So so what happens? So these dimensions behave roughly polynomial, and I'm looking for the asymptotics as I go to infinity with my k. So I'm looking for the leading coefficient here. So I take k to the d, and I'm looking for the limit as k goes to infinity. And for some reasons, I also normalize this using a constant here, which only depends on the dimension. So this is not really important. Okay, so this is the volume of a valuation, but after all, I'm interested in the volume, local volume of a singularity. So at the moment, this depends on a choice, and I want to make it independent of that choice. So what can I do? I can look for, so the infimum or minimum taking over all valuations. Of this quantity. Okay, but here I have a problem, as we heard. So you can always take positive multiple of a valuation, and this gives you again a valuation. And in particular, if you take higher multiples of v here, then it's not hard to see that actually this limit is going to go to 0. So as I take higher and higher, or multiply this with larger and larger positive numbers, then as these numbers go to infinity, actually this quantity is going to 0. So this wouldn't be a sensible definition. It would always give us 0. So it's not good. Or if I take the infimum, let me write infimum. Okay. So we need to do something. So the idea was that we want to define the volume of X in this way, and this didn't quite work. So in order to make this work, we need to normalize. And what does this mean? Okay, so we have somehow get rid of the freedom to arbitrarily resize our valuation. So we have to give it some kind of canonical length, so to say, or one of these many, many multiples of the valuation. Only one of them is the correct one. And so in order to get the correct one, so I'm going over all valuations as before. I'm taking the volume, but not of the valuation itself, but of a resized valuation. So I have to bring it to the correct length. But what is the correct length? So what is v hat, in other words? And for this, I need a second quantity called the log discrepancy of the valuation. And this already appeared, I think, also today. So log discrepancy of the valuation. And now the idea is I always rescale my valuation such that it has log discrepancy equal to 1. So this is what I want to achieve. So what I'm going to do here is I take v hat to be v rescaled by its log discrepancy. Okay, and that's my definition. And let me see how this ties in maybe with better known versions of volumes or notions of volumes. So let me collect some facts about this normalized volume. Okay, so first one. Now we consider a special case, namely we consider the cone, our singularity, to be the affine cone over the Fano variety. So Y is now projective Fano. And I take X to be the anticanonical cone over this Fano variety. Okay. Then we are in the following situation. So we have our X, and then there's a natural resolution for this X, for this singularity, for this cone singularity, which is simply given by the canonical total space of the canonical line. Okay, so, and as an exceptional divisor, we get something which is isomorphic to Y itself. Okay, and this setup comes with a natural choice of a valuation, namely the vanishing along this exceptional divisor. So our V here is just the order of vanishing along. Okay, and now the normalized volume of this valuation. Okay, I mean, the setup actually leaves us in a situation where the log discrepancy of E is equal to 1 anyway, so we don't really have to rescale. So this is just the same as the volume of this valuation. And this is just, if you like, the volume of Y, or the top self-intersection number of the anti-canonical divisor. Okay, so D here is always the dimension of my affine code. Y here has dimension D minus 1. Okay, if you like, this is version A of this remark, version B. So you can look more generally to the case of a cone singularity. And then you can look for so-called link of this cone singularity, so which is the intersection with the codimensional 1 sphere. Okay, and after the choice of the Reeb field, so-called Reeb field, so this is at least if the singularity is isolated, this is becomes or gets the structure of Sasaki manifold, and our Reeb field can also interpret it as a valuation or gives rise to a valuation, and then up to a constant, the volume of that valuation is exactly the volume of the Sasaki manifold. Okay. First remark. Second remark. So, I mean, this is just a special case. The A version is just a special case of the B version. Okay. Second remark is the following, namely that in the setup of 1A, Y is actually K semi-stable. If the following holds, namely if this valuation, which we have picked here rather arbitrarily, I mean, it's the valuation coming from this cone construction, but there are many other valuations on this cone. So Y is K semi-stable if and only if actually this valuation is the minimizer of the volume function, or the normalized volume function. So if, our vanishing order along E is the minimizer. And so this is a result by GD. Okay. And so this allows me to tick off K-stability. So I'm relating my talk now to the theme of the workshop. Okay. So let me now specialize to the situation where we have a toric singularity. Okay, so we want to look at Gorenstein toric singularity, and yeah, I want to, well, this is usually constructed from combinatorial data. how does it look like? So we start with a lattice polytope. Okay, so maybe this one. Okay, so this is my P. And then I take a so-called, or construct a so-called polyhedral cone by lifting this polytope into height 1 in the vector space at 1 dimension higher. So, and take the cone over this lifted polytope. So the picture is then looks like this. Good. So, and such a cone constructed in this way gives rise to a toric singularity, toric Gorenstein singularity. So this is the singularity we are interested in. And now I want somehow go through the steps of this definition of my normalized volume and see how this specializes in the case of toric singularities in this setup. Okay, so first we need to see what evaluation corresponds in this picture to. And it's a fact, so I can actually, it's enough to consider torus invariant valuations here, and those correspond exactly to vectors in the interior of that cone. Okay, so I pick a V which sits in the interior of that cone. And now it turns out my second step here was the rescaling. So whenever I pick a valuation, I need to rescale it to have log discrepancy equal to 1. And it turns out the rescaled valuation is actually the one which sits in the polytope. So this is the head here. Okay, so this means I can now actually consider the valuations I'm interested in as being interior points of the polytope. And this is what I'm going to do from now on. So, I mean, remember, so officially the polytope lives in the vector space 1 dimension down, but I'm taking it not too seriously. So, okay, so we now pick our valuation, and I have to say what is the volume of such a valuation. So we said this was the volume of the rescaled one. And so now this can be in fact described as a proper volume in the context of convex geometry. Namely, it's the volume of the polytope dualized with respect to this interior point. So what does this mean? Okay, so I take the volume of the polytope obtained by first shifting it by this interior point. So what I'm essentially doing is I'm just shifting the polytope such that my interior point becomes the origin of my vector space. And then the shifted polytope, there's a construction called the polar dual. And this is what I do. Okay, let me just say what this is, in case you haven't seen it before. So this consists of all U with the property that for all elements W in the shifted polytope here, the following inequality holds. Okay. So just to give one example, if this is my polytope P, and I pick a point here, oh no, I'm always doing it wrong way. Okay, so let's start here. I pick my interior point V like this, then the resulting dual polytope looks like this. Okay. Now I can try to move around the interior point and see what happens. So, and what you observe is if you move towards the boundary, so the dualization looks different. Looks something like this. And in particular, as you move to the boundary, you see that the volume becomes larger and larger. Actually, if you meet the boundary, the polar dual becomes unbounded, so you get infinite volume. Okay, so, and this is interesting because we were interested in the minimizer of this functional, right? So we were looking for the interior point which makes this quantity minimum. So, let's give this a name. So let's call it S inside the interior of P. And this actually has a name in convex geometry. It's called the Santal point. Of P. Okay, and how to think about this Santal point? I mean, I mentioned, so somehow it's a point rather in the middle of the polytope, whatever this means. I mean, in the sense, if I move to the boundary, I'm eventually get away from the Santal point, right? So it's another notion of a central point in the polytope. In general, it's different from the barycenter. Okay, so that's one thing, Santal point. And second, I can, yeah, so in other words, so putting things together is the volume of my singularity here is just the volume of the polytope dualized with respect to the Santal point. So the minimizing interior point here. Okay. And now I'm introducing another invariant here of a polytope, which is simply the product of the volume of P itself with the volume of the dual with respect to the Santal points. So the minimal dual volume in the sense I explained here. Okay, so this product again has a name. It's called the Mahler volume. Of P. And an interesting but easy to check fact is that this is an affine invariant of the polytope. So you can move it, you can apply any affine transformation, so the Mahler volume doesn't change. Okay. yeah, just one remark to connect this to my earlier remarks here. Actually, this dualized polytope you can see as a moment image of this link here with the Zasakian structure. So as you change the rate field, you change the moment map, and so the moment image will change as well, and it changes in this way, the way I described here. Okay, so here goes moment maps. Good. So yeah, so another interesting fact about this Mahler volume is that it appears in two very interesting inequalities. Okay, so first of all, so first of all, you can define the Mahler volume not just for polytopes, you can actually define it for any convex set, convex body. And you can ask, so for a given dimension, what is the maximal you can get as a Mahler volume? And it turns out this is obtained by the unit ball of this dimension. So the unit ball has the maximal possible Mahler volume for convex bodies in a given dimension. Okay, and this has a name, this inequality. It's called the Blaschke-Santal inequality. Okay, and before going further, let me just mention a few interesting consequences from this simple observation. So from this fact that you are able to connect the normalized volume with these notions from convex geometry. So the point is you can now apply knowledge from convex geometry to the situation and hope to learn something about normalized volumes, and you can learn something. The first one is a very simple application of this Blaschke-Santal inequality. You can show using this that toric singularities are bounded once you bound the normalized volume away from zero. So just put it like this. Of toric singularities. So in fact, this just means once you say, I want my toric singularities to have normalized volume at least epsilon, then there are only finitely many toric singularities left in this dimension. Okay, so this is not so impressive anymore. So a few weeks ago, I think there was a paper by Sheng Yang and Zikan. So actually, you get such a boundedness result in general. Not just for toric ones. That's what I'm saying. Okay. So we will hear more about this tomorrow, I guess. Okay, but then you can also prove the ODP gap conjecture for the special case of toric varieties using somehow known facts about the Mahler volume. So okay, and both these results were joint work with Joaqu&iacute. Okay, but this is not the main point of today's talk. So main point of today's talk is a inequality in the other direction. So we now want to bound the Mahler volume from below, and it turns out the convex body with the minimal possible Mahler volume is supposed to be the standard simplex. But this is just a conjecture at the moment. Actually goes by the name Mahler conjecture or non-symmetric Mahler conjecture. Okay, and this is known only up to dimension 2. And so it's not hard to calculate the Mahler volume of the simplex. And if you know toric geometry, you know the Mahler volume, or it's related, the simplex is related to the smooth point. So this is exactly the normalized volume of the smooth point, which is d to the d. Okay. Which is a little bit surprising that it appears on the left-hand side of this inequality. So there's another fact which I didn't mention. So the smooth point is actually gives you the maximal possible normalized volume. Good. So, and the remainder of this talk will deal with the question, does this give rise to any sensible inequality in algebraic geometry?
I'm a bit confused about your notation. So D is the dimension of...
Sorry, yeah. Okay, I'm confused myself. So D is always the dimension of the singularity, but because of my setup, D minus 1 is actually the dimension of the polytope. Yeah, thank you.
Then what is the Mahler volume on the left? Is it still D to the D?
It's still D to the D, yeah. Okay. So yeah, I want to discuss what could this be. And to get an idea, we should go back to our toric setup. Right. Yeah, so let me just remind you what the Mahler volume was in this setup. So it was the volume of P itself with the volume of the dual of P with respect to the Santal point. And so my aim is now to give a meaning to this product in algebraic geometry. I mean, one of the factors we already discussed, right? So one of the factors is our normalized volume. Of the corresponding singularity. But what is this going to be? I mean, so what is a sensible interpretation of this quantity in algebraic geometry? And so we ask how to interpret the volume of the polytope which went into the construction of our toric singularity. Okay, there are many possible answers, of course, but one may be quite sensible and obvious is to relate this to resolutions of singularities. Okay, so in the toric world, a resolution of singularities is just a subdivision of the cone into simplicial cones. And in this setup, this is equivalent with subdivision of my polytope into simplices. And in order so that the pieces give rise to smooth varieties, I want those simplices to have volume equal to 1. Right? So this means I'm looking for a resolution of singularities. I'm looking at a triangulation of my polytopes such that all triangles have volume equal to 1. So this means counting the number of triangles is equal to the volume of the polytope. And what does this mean? What is the algebraic geometric the meaning in algebraic geometry of the number of simplicial cones in the resolution? It coincides with the Euler characteristic of the resolution. Okay, so this means a first idea here could be to interpret this as the Euler characteristic of actually a so-called crebant resolution of X with the normalized volume. Okay, so a question which arises do we have like an inequality like in the Mahler conjecture for this quantity? Okay, so question, do we have this inequality here? In general. I mean, in the toric setting, this is equivalent with the Mahler conjecture. The question is, do we have such, or is it sensible to maybe conjecture such an inequality outside of the toric world? Okay, and now I'm looking at an example telling you, no, it's not sensible. Not in this version. Okay, so another example. Look at a quotient singularity. This should be D. So quotient by a finite group. So then what we learned today is that the normalized volume of this quotient singularity is just the normalized volume of the smooth point divided by the order of the group. Okay, what do we get for the Euler characteristic of the resolution? So it turns out this is just the number of irreducible representations of this finite group. Okay, but the number of irreducible representations is in general strictly smaller than the order of the group. So we have the order of the group is the sum of Ri squared, where the Ri are the ranks of the irreducible representations. So this is a standard fact from representation theory of finite groups. So we are summing over all irreducible representations, and for each irreducible representations, we take the rank of this representation and its square. I mean, this is clearly larger than the number of representations, which we just said is equal to the Euler characteristic of the resolution. Right? I mean, there's a case where you have equality here, namely if the group is abelian, then all the irreducible representations have rank 1. Okay. But this tells you in general, once you are not abelian, you have a strict inequality here, and then this cannot hold, because what has to go here is at least the order of G, right? So we figured out the volume of X is this. In order to get something which is larger than d to the d, you have to multiply it with at least the order of our group. So, but we have seen that the Euler characteristic of the resolution is in general strictly smaller than the order of our group. Okay. So how to repair this? Okay, and I mean, actually in the complete second part of my talk, I'm not presenting any results. I'm just speculating. So I hope you're happy with this. So let us speculate what could be a reasonable replacement of this Euler characteristic by looking at our examples. Okay, so what we could do is, I mean, for this particular case of a quotient singularity by a finite group, we need maybe an interpretation of this quantity, right? So we need to make sense to this, what this quantity means, even if we have a singularity which is not a quotient singularity, right? So for quotient singularities, it's fine. It's just the order of the group, but we want to get an inequality for general singularities. So there's no group order. What could this be in the general setting? Okay, let me move to this point. And so the idea is to move away from resolutions of singularities as we know them. So geometric resolutions of singularity and moving to so-called non-commutative resolutions. Of singularities. So what's the idea? Okay, so we have our coordinate ring of a singularity, and how to understand, how to introduce a notion of a non-commutative resolution, which is after that. Okay, so I will be very, not very precise here, but I hope I will be able to present the idea at least. So it comes with M being a reflexive R module. Okay, and so the idea is to come up with an R module such that the endomorphism algebra of that module is better than the commutative ring we started with. So the point is, if you move to the endomorphism ring of a module, this thing is not longer commutative, right? So the multiplication is composition of homomorphisms. So you replace a seemingly nice object, a commutative ring, by a not so nice object, a non-commutative ring. So you have to gain something from it. And the idea is what you gain is this becomes in some sense a regular, but now non-commutative ring. Okay, so I'm not really, so regular is the wrong word, but a ring with nice properties. Okay, so I want this to be nice. Okay, and now given such an M, you can ask for the direct summons of this M. So I want to write my M as or decompose it into direct summons. And I want that those direct summons Mi and Mj are pairwise non-isomorphic. Okay, so I have, no, this is not, let me give this different names, S1 up to SL. And now, in the case of a quotient singularity, this allows us to connect this to what we did earlier. So in this case, we get such a non-commutative creep-in resolution from the representation theory of the group. So in this case, Mi correspond to, so each of those direct summons corresponds to one irreducible representation. Let's call it Vi of G. And actually the ranks coincide. So rank of Mi is equal to the rank of Vi. So what one could ask, or what this maybe suggests, I don't know, is to repair our question, namely, does the following inequality hold? So we take such a non-commutative resolution and we sum up the ranks of the Mi or their squares respectively. And the question is this now always at least d to the d? Okay, and this is just a question. I don't have an answer. Let me just say what we know. So for the toric case, you somehow expect that, which is not true in general, but it's true in dimension 3, that these MIs have all rank 1. So we actually get back to just the number of summons here, and the number of summons is again expected to be the Euler characteristic, which again is known in dimension 3. So actually, this inequality for the toric case, at least in dimension 3, becomes just the Mahler conjecture. So what is known? Then the case of quotient singularities. I mean, we set up everything such that it just works for quotient singularities. To be more precise, for a quotient singularity, we get actually equality in this inequality. That works for quotient singularities. And I mean, I tested it for every singularity I could get my hands on, and where I also knew the non-commutative group and resolution, which doesn't mean much because I don't know much about it, and it's only known in a few cases. So, so it looked good, let's say. And so let me finish with one more example here. Those are cones over the Petzl surfaces, so anti-canonical cones. And actually, so there something like this was observed some time ago already by Moraga. And what is the picture here? In a slightly different language, to be honest. So, what is the situation here? So for the Petzl surfaces, so for the toric ones, it's I covered this already. Yeah. So actually, Mahler conjecture in dimension 2 is proved. So it's for sure true for toric Petzl surfaces. So the interesting one are the non-toric ones. Okay, and there is kind of a classification of those non-commutative group and resolutions. And they are classified by solutions of equations of Markov type. And so here for degree 5, degree 5, 4, 3, 2, and 1, which are the degrees which are not toric. There's always one or even several of those Markov type equations. And the setup is always, I have only 3 different ranks which appear as ranks of my summands here. And those ranks are the variables. So a possible rank is x, another possible rank is y, and a third possible rank is z. And so I have one of the rank given by x, I have one summand with the rank given by y, and I have 5 summands with the rank given by z. So what the left-hand side of this equation is exactly this sum here. Okay? And now what I'm going to do is I'm testing here this product. So I'm testing the volume multiplied with the right-hand side or the left-hand side of this equation, and see what I get for solutions of those Markov equations. So each of those Markov equations has a minimal solution. So this is here, it's this one. So for x equal 1, y equal to 2, and z equal to 1. And if I'm playing this game, then I get 50. Okay, I can do this for all those known minimal solutions, which gives rise to the minimal number I can get in this product for non-commutative creep-and resolution. And the point is, okay, so they are all bigger than 27, which is exactly 3 to the power of 3. Okay, so the minimal ones are 27, which are our lower bound here. Okay, so this doesn't look so bad. And yeah, so I think it's something worth to look into in more detail. That's what I'm doing now. But yeah, I'm at the end of my talk. Thank you for your attention.
Thank you so much. Is there any question or comment?
Excuse me? Why that is called the non-commutative resolution? I mean, where's the resolution?
I mean, okay, it's a very good question. There is like from the algebraic point of view, it's very natural, right? So you resolve it because you replace your commutative but singular object by a non-commutative. Okay, wait, I forgot something to mention, but you replace it by a non-commutative, but in some sense non-singular object. And I didn't specify what non-singular means. Okay, it's a little bit more complicated, but so this one is in some sense non-singular, but, and this is what I forgot to mention, it also naturally contains R as a commutative subring and actually as its center. So how to see this? I mean, just multiplication with the ring element gives you a particular endomorphism of your module, right? And this gives you this inclusion. And yeah, so in this way, you can see this as a resolution of this singular object. But actually, this is not just, so algebraists just didn't make this up, but there's actually a direct connection to geometric resolutions of singularities. So, for example, in dimension 3, you know there's a non-commutative creep-and resolution if and only if there's a creep-and resolution, and there are also ways to construct one from the other. So it's not just, it's not really outside the world of resolutions in algebraic geometry. It fits very well into this story.
Regarding your question, is there something like the book on Newman type inequality, like a weaker version of it? Do you know anything like weaker than that?
I don't know.
All right.
Is there any other question or comment? No, it's fine. Keep going.